Greetings. My name is Dr. Mohammed Nizami. I'm coming to you from Jerash, Jordan, background there. I welcome you to my lecture. This is the part three of several lectures that I have on the RF receivers that are directly sampled from the antenna after amplification and filtering, or analog to digital converter, direct sampled RF receivers. And today is part three. Now, previously, I have covered the two parts that I have covered. You can refer back to them right here, part one and part two. Please go back and to my YouTube channel and watch those before you watch this part, because they're really a series. I have a whole bunch of other topics that I've covered in the past. You can look here and see advanced, um, basically active and passive antennas, filters, combiners, power splitting, and so forth. You can see there's a whole bunch of Ka, Ku band, and C band, S band transceivers, antenna arrays, beamforming, RF transitions, so on. So today, so the channel address is right here. Okay, you can refer back to it. I would appreciate if you can please visit the channel and subscribe, because subscription really keeps me motivated, knowing that there are more people and more people every day that are interested and to go on. And please do make comments. Now, today's lecture, I have altered it from the previous plan based on your feedback comments that I've got on the part one and part two. So when you comment and when you suggest, that really also enhances the topic that I'm covering. You could reach me at this number here. This is also has a WhatsApp and Telegram Android app on it. This is my email. You can also reach me via email. I'm also on LinkedIn, so you can just type my name, Mohammed Nizami, as spelled right here. Okay, so this is the outlines of the from part one and two and three today. So previously we have covered these concepts in here. Today I'm just going to go further into the principles of the direct RF sample receiver, and then look at the ADCs and SERDES associated with them that are available commercially. And we're going to go two examples, okay, to illustrate the concept of subsampling, or the sampling a signal with a sampling frequency that's way lower than the actual carrier frequency. And that's called subsampling or undersample. I'm just going to cover two system examples. One that is S-band receiver at 2800 megahertz, and the other one is 28 gigahertz. So, okay, so 100 times the frequency. Okay, so I'm going to go through this, and so the plan is that we want to survey this and eventually get to the point where I talk about the basically about the how do you design this chain, okay? How do you distribute the gains, the noise figures? How do you model the A to D as part of an RF chain with an associated noise figure as well? Okay, so the slide here is what it's all about. So what we're talking about is really RF to bits, meaning we're not going through an intermediate frequency conversion, be it a single conversion or multiple conversions or even direct conversion receivers. We're not doing that. We're eliminating the local oscillator, LO, and the mixer. And the design approach is not anymore based on the MN, the LO frequency plus minus the and of the RF carrier. Okay, so there's little differences in the approach that we take to design this, and starting next week, I mean next section, next session, next lecture, we will go deeper and deeper into the until I basically come to the point where we have a common methodology to design these so that you can accommodate a design from, say, VHF all the way to millimeters, okay? Without having any frequency translations. But beyond that, of course, you really have to have a, um, a frequency translation so you can bring the frequency down so you can utilize the commercially available ADCs, analog digital converters. Now, there are some exotic products out there that digitizes at rates way above, I would say about 20 megasamples per second, all the way to 60 gigasamples per second. But of course, those are very expensive, and they're not really geared toward commercial use. Okay. All right, so let's go further. Now, one of the feedback that I got from part one and part two, a lot of people are not really still not not seeing the picture of how do you really directly sample an RF carrier, say at 28 gigahertz using 10.8 gigasamples per second, for instance. To them, it seems like they still have the idea that, wait a minute, to sample a signal and recover it in the digital domain, you really have to sample it twice the frequency. And that's not true, really, because it is true for the information bandwidth, but not the carrier. The carrier can be anywhere. And we're going to show, I added this slide here purposely to refresh your mind, just in case if you have forgotten some of the basic principles of signal sampling or digitization of analog signals from even undergraduate system class, okay? So when you have an ADD, you have two signals, basically. You have the signal, the analog signal that you're trying to sample, and you have the sampling frequency that you drive the ADT with, okay? And usually this here is really a train of impulses that are uniformly spaced in time, because every time you pulse the ADD, basically on the rising edge or the falling edge, you're making a sample. And to mathematically, that's really a convolution process. So what you're doing, the information in the digital domain really is really a convolution between the sequence of the samples that are coming in from the analog signal in time, discretized time, convolved with an impulse function. And the impulse function now in here, it's not a single one, but it is really a series of combination from minus infinity to plus infinity, okay? So all we're doing is we're taking the analog signal and convolving it with basically the impulse function. And of course, if you recall, now this is discrete time definition, but really in the frequency domain, the convolution is simply really taking the Fourier transform of the analog signal and taking the Fourier transform of the impulse function and just basically multiplying them together, okay? And that has a simple definition that basically when you convolve a signal or an impulse, it's really that same signal at the impulse instant, okay? And this is really the mathematical principle of the ADD RF direct sampling of signals. And so to illustrate this, let's look at this diagram. Okay, so let's assume that X of n is basically some kind of bandpass signal at some carrier frequency, FC. Okay, in the frequency domain, this is the representation of that sequence. Okay, now the train of impulses basically is really, which is the sampling frequency. Okay, nothing but a train of impulses that are distributed uniformly at a space which is Fs. So the first train is at DC, the second one is at Fs, the third one is at twice Fs and 3 times Fs, and so on. And we have the mirror image as well. Now, what we're doing really here when we're digitizing a signal, we're really convolving this signal with this. Now, notice here that the Fs, I did not specify where the Fs here, I did not specify frequency, but the frequency is much less the center frequency of the modulated signal. This signal in here has a bandwidth which is delta F, okay, which is the width of the bandwidth, the information bandwidth that are placed on that carrier. And so therefore, when you convolve this with this, it's really splitting this summation into an individual points for the M indices in here. And the M indices, of course, in here is 0, 1, 2, 3, and so forth, which is the harmonics of the Fs. And then you also have the negative image of that operating on here. So when you do, let's assume for the first one, which is at 0, okay, which is this one here, what we're doing is we're evaluating this at M equals 0, and that's basically the same thing. So we're just copying the same signal here. Now for this, for the negative one, okay, -1, we're going to do this side and then come back and do this side. For the negative one, okay, which is this one, we convolve this one with these here, and all this is going to do is when you have a delta impulse convolved with a sine wave, okay, of some sort, you really become, it's just a time shift. If you look at the Fourier transform of this time, this, it's really shifting this down by exactly the same offset that is here. So this is at indices -1. At -2, we shift it down. So we can see here's the top one, but the bottom one went off the screen. It really went around and will come back eventually on this side, depending on the spacing of FC. So so the other one disappeared, but you still see this one. Now let's start on the positive side. Again, we shift upward. These two, we shift them upward. So you've got these two. And so second one, we have the lower one is here, right before 0. And then the second one went off the screen, okay, off the scale. And of course, the third one is the same thing. This went up to this frequencies, and the other one went up out of the screen. Now, of course, it's a summation of these. So when you sum these here, you end up with this. And when you look at this, really, your information is this one here or this one, either one. It doesn't matter. This is the same as this, except it's mirror image. So this has inverted spectrum, meaning the lower frequency portion of the information on this side here, it's on the higher side. Okay, and so and vice versa. So when you do this, you realize, wait a minute. Now, what happened is when you convolve these here, the subsampling, you get the same information, even though it's a lower sampling frequency than the carrier itself. You get them distributed over the Nyquist zones, which we defined in the last lecture. So therefore, you can come in your digital domain here, and you say, I want to pick any of these that are appropriately for myself. You either using a filter or using a decimation process or using frequency rotation, digital down converter. So you can come in here and utilize a digital down converter to bring this one right to here. The whole series will shift down also, and then filter out just that one alone. Okay, so this is really, so now what happened then, this will work. You can recover the information on one condition, is if these here don't overlap. How do these overlap? Well, they will overlap depending on how wide the delta F and how far is the center of this band here from the sample frequency. And that, of course, to guarantee that will not happen, as you can see it right here, I want to make sure that Fs over 2 in here, okay, is that this one doesn't come close so that overlaps on this one. And that's the condition, Nyquist condition, which says that the F sampling frequency has to be at least twice delta F, and it has nothing to do with the carrier. So the carrier can be at 28 gigahertz, but the sampling frequency doesn't have to be that. All it has to be is that it has to be more than twice the bandwidth. If the bandwidth of your information in here is 28 gigahertz plus minus 100 megahertz, so 200 megahertz of information bandwidth, your modulations, then all you need to do is just sample it at a frequency that is higher than 200 megahertz, and you'll be able to cover these ones, just as an example, pictures example. Or if you solve for delta F, that means the bandwidth has to be less than Fs over 2, and that you can see it right here. So this is Fs over 2. I want the bandwidth of this sideband in here to be less than that, because otherwise it will spill over onto the next Nyquist zone and will alias, and we don't want that to happen. So today, let's look at one of the examples. So if you have a 2800 megahertz signal that you're receiving on an antenna, and you have an ADD running at 3 gigasamples per second, we can work out in the next session. I'll show you how we can work out the details of the design of this chain, because we have to design this chain just like we did design conventional heterodyne and high IF sampled receivers, meaning we have to design it based on the required signal to noise ratio at the DMOD on this side, at the third intercept point, the second order intercept point, the linearity of the front end, the sensitivity, the noise figure, the overall gain, the image rejection, and so forth and so forth. All of these will have to be incorporated. So now, if you sample a signal at 2.8 gigahertz using a 3 gigasamples per second ADC, what happens is your information will be in the information that is going to be in the first Nyquist zone, which is from 0 to 1500 megahertz, or 1.5 gigahertz, and that's the definition of the first Nyquist zone. We know that it's going to be just a subtraction of these two here. So this is the formula. So the digital IF, DIF, is always going to be some n, n is an integer, 0, 1, 2, 3, infinity, times the sampling frequency minus the analog signal, the incoming analog signal. So if you substitute here 2.8 gigahertz, and in here 3 gigahertz, and n, you start varying in until you find which one fits right here. The first one that will come, and we'll go through this computation later, we'll say more about this, is that your digital IF in here, if you take the FFT of this ADD signal in here without any filtering, it's going to be centered at 200 megahertz, okay? And that's going to be basically this signal here, except it's got synthetically frequency translated to the center frequency of 200 megahertz, okay? Now, of course, your ADD, which I will show you today, or if it's an older ADD, has a digital down converter, which is nothing but a direct digital synthesizer that you program to any frequency, and mathematically you actually multiply, which you rotate this signal to anywhere you want. So we're going to rotate it to 0 hertz because we want baseband. So we can have our DMOD decode this signal in here. And that's basically what happens. Now, in some cases, the DMOD in here will have a feedback to here, to the NCO, because a lot of times if you're dealing with a Doppler shifted signal, or a signal that has some kind of frequency inaccuracy with it, or you want to translate it to another frequency, you can always feed it back here and actually do the tracking in here. So you can estimate the offset from your preamples and so on the signal, preamples and midamples, whatever, and then figure out how much you need to shift that signal, that baseband here. So if there's an error, you can introduce it so that you're getting rid of that offset, so that you're sitting exactly at 0 hertz. All right, now likewise, let's do it 28 gigahertz. 28 gigahertz, I'm going to do with 12.8 gigasamples per second, which happens to be, this is a sampling frequency that this here E to V device. Now we don't have to go with E to V. There's analog device and TI devices that we could utilize. But for right now, we're just saying, or even AMD Xilinx system on a chip, the SOC, out of SOC. So we program it to this frequency. And what happens now, these two here, if you apply this formula in here, FS is 12.8 gigahertz and analog signal is 28 gigahertz, and N, you vary the N, it turns out, and of course your Nyquist zone is between 0 and 6.4 gigahertz, which is half of this frequency. That's the definition of that first one. It turns out your IF, digital IF, is going to be at 2.4 gigahertz. So you did digitize it correctly without any frequency translation, but your information, the lowest one that sits in the lowest Nyquist zone, is really sitting at 2.4. And therefore, now you want to translate that to baseband. So all you need to do is just rotate it with the numerical controlled oscillator in CO. You program that. That's basically sits into the AD, and there is a whole bunch of filtering in here that takes place right after this, because as you know, like I showed here, you're going to end up with multiples. So when you shift that signal down to the center in here, you need to get rid of the adjacent replicas. And we do that with filtering. All right, so let's do a survey on the available devices out there commercially. I'm not going to go into the exotic. I know there is a whole bunch of companies out there, startups and some companies that are actually offering ADDs that run at tremendous sample rate, up to 50, 60 gigasamples per second. And those are, those are for geared toward systems that are not commercially priced. These are for airspace or experimental and so forth. But our focus is to look at the spectrum for the all the 6G and the spectrum for the SATCOM and survey it and look at the what is the frequency, what are the ADDs out there that are available. Okay, so if you look at the FR1 and FR2 frequencies for 6G, and we're going to look at also the SATCOM, KU and KA band, and C band, what you can see is that there are these bands are named with ends and some numbers between 1 and 261 in this case. And then you can see that these bands are placed, in conventional cellular bands, and then you got the S band, some C bands, and so of course you got the Wi-Fi, which is at 5,800 megahertz and 2,400 megahertz. And then you've got some that are at 600 megahertz and 700 megahertz, 1,700 megahertz. And you can go up, let's see, 4 gigahertz also. And of course, you've got the FR2, which are really the bands that are millimeter bands. And you can see that we have up to 28 gigahertz and 29 gigahertz even. There's one in here. In these cases in here, now, currently with ADDs that are available that we're going to survey, I'm going to go through the survey of those. You could very much use them to sample directly out of sample these. Now, with sampling frequencies up to like 12 gigasamples per second. If you use 12 gigasamples per second, you are able to actually directly out of sample these signals in here. For the rest of these here, most of them really, you could look at them and see that most of them, you probably can cover them with some of the devices that are readily available from analog devices and Texas Instruments or Xilinx, well, AMD nowadays, um, that utilizes basically up to like 4 gigasamples per second. Um, Very much you can subsample any of these frequencies. So it looks like really the trend in this year, 2025, of course, I don't want somebody to watch this in 10 years from now and realize, wait a minute, what is this? Very primitive. Well, in this year that we are in, when I will show you in the next slides, you'll realize there are two sets of ADDs, some that are running in the up to like 4 gigasamples per second, and some that are running up to like 12 gigasamples per second. So it's very much that with the 4 gigasamples per second, you can subsample most of the LTE and FR1 bands. And of course the bandwidth, there is hardly only two services that I saw with a bandwidth more than a gigahertz. Okay, most of the bandwidths are in the hundreds of megahertz and readily available in the ADDs. Okay, and most of these ADDs that are sampling at 4 gigasamples per second, they cover up to like 8 gigahertz 3 dB bandwidth. So they are appropriate for the FR1. For FR2, you need to move up to one of the, without any frequency translation, of course, any frequency down conversion, you need to utilize one of the ones that do 12 gigasamples per second, and those have 3 dB bandwidth of on the order of more than 30 gigahertz. Okay, of course, the signal to noise ratio and the effective number of bits is not as good as the lower ones, but we will in the next sessions we will look at that closer. Okay, now the SATCOM very much. I didn't cover that slide. I should have had a slide for the KA and KU band. I will try to put it on the next section, but it's very much like the millimeter one. So even the KU band, we need to utilize the 12 gigasamples per second devices. Okay. All right. So this is just a pictorially representation. And what I'm doing here is I'm looking at the just the other services in the lower FR1, namely GPS, both L2 and L1 bands, the Bluetooth, Wi-Fi, both the 5800, the 5.8 gigahertz and 2.4 gigahertz, and the cellular. Most of this stuff you really can do with a sampling frequency at 4 gigasamples per second. So if you get an ADD, which I will show you, these are readily from TI and analog devices and AMD. If you have a bandwidth of, say, more than 6 gigahertz, you're able to see all of these signals. You can digitize them. So all of these bands from 0 hertz to 6 gig, you can subsample them with a sampling frequency at 4 gigasamples per second. And of course, the alias, you need to figure out where the alias ends up being, and so you can shift it and do that. So you could very much, like I showed in here, for instance, you could figure out, you can have multiples of these services, and you're digitizing simultaneously, and you can see the spectrum, and then you can do channelization in the DSP domain using FIR filters in conjunction with digital down conversion. Okay. All right. So let's go further. So this here is I try to find one. We've got ADCs and AD with the numbers. These are the ADDs. TI uses ADC, and ADI or analog devices uses AD. Okay, and then the front end, integrated front end, which has a ADD and DAC, they utilize AFE on there. Okay, so you can see that we're somewhere between 12 and, or maybe from 10 to 14 bits. This is where we're really going to be trying to be. And we've got this one in here, of course, at 10.4 gigasamples per second. These are the model numbers. These are device numbers. And so you can see that this one here, you can run it at 10.4 gigasamples per second, but it's only 8 bits. Okay. And this is the resolution in bits. You can run this one at 10.4 gigasamples per second. This is 12 bits. Okay. So you can see that this one here can be utilized for the millimeter ones, but for the other ones, you could utilize very much this one here at 5.2 gigasamples per second. Okay. And of course, all of these ADDs are equipped with the SERDES, that is the GSD 204B and C. Okay. So we'll talk about that in a minute. Okay. So these are the companies that are right now the big players in this market, like I mentioned before. Okay, if you look at these devices, I'm just taking this device as an example right now. Oh, okay. If you look at this device, it's a 14-bit device at 3 gigasamples per second, and the model number is ADC32RF45. Okay. And I noticed that the ADCs, when it has RF with the model number, it usually means it's an RF direct sampling ADD. Okay. And so if you, this is from Texas Instruments. Like I said, Texas Instruments use the abbreviation ADC and then some numbering scheme, where analog devices uses AD, as you'll see in a minute. For instance, let's look at this is AD, as you can see. This is analog devices here. Okay. So if you look at these devices, usually they are all are the same thing. You've got these sections are divided like this right here. The first thing is, of course, we've got the ADD, array of an ADD, digital analog to digital conversions. And then before that, we've got some kind of interface, analog interface, which is usually a differential. And that's basically, I covered that in the previous sessions on designing high-speed optoelectronic front-end design, where I covered this heavily. So you can see, which is very critical, by the way, this front-end design. This is integrated inside, of course. And then after the ADD in here, you have interleaved ADDs to offer high speed. We have numerical controlled oscillators and digital down conversion. Okay, it's really this is not NCOs only. This is a typo. They should correct this. It's really NCOM, which means numerical controlled oscillator and multiplier, which means it's really a digital down conversion. Okay, so you've got a bunch of you get some kind of sync reference signal. There's a phase lock loop internally that creates, and there's a clock reference that creates the CW in the digital domain that basically brings these samples to some frequency shift, which is presumably to baseband. And right after that, there's a some kind of um, uh, low pass filter. Okay, and the reason we have this is because remember what I said here. When you when you sample this, there is a whole multiple of them, and so this one in here, there's no signal here at baseband, because a baseband means its center frequency is 0 hertz. So what we need to do, we need to digital down convert one of these anywhere in here. And of course, you don't care if it's this inclined ceiling in here means the inversion. This is to keep track of which one is inverted. The inversion process, spectrum inversion in the digital domain is pretty simple, done. Okay, it's just signs changes on the I's and Q's. So when we shift this, we need to get rid of the other crap in there, the other replicas, And that's basically what you're really seeing in here, in these ones. And of course, right after that, after we do that, we need to simultaneously filter and decimate because we are oversampling. This is um, gigasamples per seconds, and we're trying to recover a bandwidth on the order of hundreds of megahertz at most. Okay, and so therefore we don't need all of those samples, and that why we have so many sample rate, which is gigantic, is just to overcome the fact that you really want to separate the images in here, the replicas in here. You need to run FS so high to be able to get these away from each other so you can recover one of them using digital down conversion. And so therefore, right after you digitize and bring it to baseband, at this point, you're not interested in having samples, gigasamples per second. All you need is just twice the rate, that is twice the bandwidth of the information, just to recover this signal here. This signal in here, the bandwidth of the information is hundreds of megahertz, tens of megahertz sometimes, even kilohertz for narrowband comp stuff. So therefore, we need to decimate. So you've got decimation and filtering to do that. And of course, right after that, you're ready to move your digitized samples to the next word, which is where your digital demodulation and decoding, deciphering, packetizing, and so on. Okay, so this is what you got. You got this in here. Of course, this dual channel, and there's other stuff in there. The serial peripheral interface on there. Of course, the GSD interface. This is a standard that is either 204B or C, and we will get to that in a moment. This is a newer standard. It used to be the differential voltage one, which LVDS, but that can handle only lower speed data. So this is intended for up to like 12 gigabit per second. Okay, packetized and sent to the demodulator. When we look at this if it happens that I cover this in the for the transmitter section, everything that you see in here has to be done in reverse. Like in here, this decimation is going to be interpolation because you need to fill in more and more to move, and this will be a digital to analog converter. Okay, and this will be reversed to the other side, which is a buffer. So just keep that in mind. Okay, so here's another example of these devices. So this device has a quad of these, and they can sample the ADD section. This is intended for transmitter or receiver in the same package, okay? But the speed in here is 3 gigasamples per second. The frequency range, of course, is from up to 12 gigahertz, okay? So this is very good. So you can, this here, and in this one, the bandwidth of this is 4 gigahertz, okay? So this one here is a little bit lower than this, even though this one is a lower sampling frequency. Another one in here is this device in here. This is a 4 gigasamples per second, and the 3D bandwidth is 8 gigahertz. So this is a beautiful one. And this is from ADI, analog devices. And so you can see here, as you can see, the ADDs in here is basically, this is the input. And the first thing you see is there's a finite impulse response filter right at the output of the ADDs that you can filter your samples, and then you can adjust the delays between these. And this is the purpose of this is because for systems that are like phased array systems where you're trying to coherently obtain a reference that is fixed and no timing error between them. And then, of course, you got the digital down converter, and they've got two stages of digital down converter in here. The first one is coarse, meaning you do it at a higher speed, translation, but it's not accurate. There's a little frequency offset along with that. And what you do, you have another fine um, digital down conversion in here. And then, of course, you got the GSIC, GASD 204 or 204C, B or C. Now, this device in here just happens to be because it's 12-bit. You can see we're displaying in here. In this diagram in here, I will utilize this in the next sessions when we start looking at the receiver chain design, the budget link from antenna to the ADD. You can see that you're driving. This gives you the signal to noise ratio and spurious-free dynamic range as a function of the input relative to the full scale of the ADD. And next session we will define what that is. But it's basically the level where the ADD gets saturated all once. Okay, and so as if we back the input drive from to the ADD, you can see that the signal to noise ratio and spurious-free dynamic range changes, so we need to make sure that how do you drive the ADD, what ranges, and that's going to be covered in the next sessions as well. So you can see that the spurious-free dynamic range is constant throughout, but the signal to noise ratio relative to the carrier and to the full scale both vary. Okay. All right, here's another one which is running at, and this is AD, that's analog devices. Same thing, you've got this one runs at 10.25 gigasamples per second. So you can see here they tested this with 2.6 gigahertz. Let me go back and see. This was tested at 7.2 gigahertz. So this result in here. This result in here was tested at 2.6 gigahertz at 10 gigasamples per second. And you can see that it's pretty good. All right, so this one is the same thing, okay, except it does have some options where you can bypass the digital down converter, for instance. And this is good in some cases where you want to do the digital down conversion in the FPGA. There are some functions that I forgot to tell you about in here. Like, for instance, in here, you can have some DC offset removal or some correction and so forth. There are some adjustments, tweaking buttons that you can have. Like in this one in here, for instance, you have an AGC digital gain in here. So you can actually scale and multiply constant or vary the signal level in the digital domain before it goes on to the air. All right, here's another one from TI at 10.4 gigasamples per second. Okay, and this one has a bandwidth. Let's see, the bandwidth is 8 gigahertz as well. So all of these systems are very good for these services in here for FR1. Okay, and for C-band SATCOM. They're not for KU and KA. You need tens of gigasamples per second. All right, so okay, here we come to this one here. This one is a newer device, 20 gigasamples per second. Okay, so this is a huge jump. And you can see the instantaneous bandwidth is 10 gigahertz as well. Okay, so now we come to here. This is the E to V Teledyne, 12.8 gigasamples per second. And you can see they gave you some test results depending on the input. And you can see for the 28 gigahertz, the spurious-free dynamic range is 44 dBc. And the second harmonic and third harmonic, one is minus 50 dBc full scale, and the other one is 70 dB below full scale. Now, these harmonics, we'll talk about that next week, because this is part of the frequency planning that we have to do for the ADD. Remember, the direct RF sampled receivers, we don't have a mixer, so there is no frequency planning in terms of LO, spurious, and harmonics versus the carrier, the RF carrier signal. But what we have to do, we have to worry about the ADD now has an interleaver on it because there are multiple of them, and there's mismatches between those, and you get spuriouses from the interleavers, spuriouses from the mismatches between the ADDs, and you've got harmonics of the RF itself. And when those go in, okay, when those creep into the signal and you start rotating the frequency, we have to keep track of them because some of them will go around an alias and come back right back in band. So there's a frequency planning aspect of this, and there are some spreadsheet calculators that you can utilize to do the frequency planning, and we'll look at that next week. So now Xilinx has, you all know, has the out of sock, and very much the same thing. In fact, when you look at these devices in here, in the past, it used to be an ADD, just basically that's it. But now it included all of these functions. And there are years and years of work of people that spent doing this stuff inside FPGAs, because I mean, I worked on systems where the ADD passed the samples to the FPGA, and the FPGA, inside the FPGA is where you have to design all of this in here using hand VHDL or Vivado built-in blocks. And so there's tremendous work. This used to be, so it's a blessing to see that all of this work, these people from TI and ADI took this work and put it into this ADD device. And in fact, it's not really a simple ADD converter anymore. It's really a receiver chip in that sense, okay? All right, so Xilinx, in Xilinx, you can go in and they have a variety of these, and you can see they have an array of these. You can purchase these devices, these sync devices, with ADDs on there that are up to, you can see them here, 6 gigasamples per second for this generation here. They may have gone even beyond this. So, okay. And the bandwidth is 7 gigahertz. So they are competing one-to-one with these people in here. But of course, now when you got an FPGA, now that gives the benefit of that is that you can build your modem into the FPGA as well. So you're really the out of sock itself has the complete modem in there. And that has benefits. So here's an example from the literature of Xilinx showing the out of sock, basically how you utilize it in a transceiver at the FR1 frequencies. And they gave you the devices. This is 3.75 gigahertz. So very much just like on the ADD, so you need the intermediate batch between the ADD and the antenna, and it's directly connected, as you can see. So there's nothing but amplifiers, low noise amplifiers, and filters, and then a balun in there. Okay, and then you have basically a complete set of modem functions. So when you utilize one of these ICs, you don't get that benefit. You come to here and then you still have to jump over, go to an FPGA or an ARM processor and do your demodulation. In here, in the FPGA, you really have it in here, okay? So they may have digital pre-distortion like you have in here. I'm sorry, right here. You have a digital down conversion. You have an AGC. You have a whole OFDM receiver, okay, where you have digital down converter, your FFT, and you go into recovery of data directly from the carrier. All right, so having said this, now let's go further and look at some of these just to see now. So we have these. Now you can see that all of these devices in here are available for you from these various sources, and you can come back and figure out basically how to design these systems. So next, what I'm going to do is I'm going to stop right here, and then we're going to go further, trying to look at actually how do you utilize these devices into direct RF sampling from the antenna. Okay, so I'll stop right here, and I will see you in the next um,